All right, let's dive right into one of nature's most powerful and frankly terrifying forces, earthquakes. We're going to get into what causes them, how we measure them, and what it all means for us living on this surprisingly shaky planet. Let's get to it.
I mean, it's a pretty fundamental question, right? We take for granted that the ground under us is, well, solid. So what on earth happens that can make it shake so violently? That's exactly what we're here to break down.
Okay, so first things first, we need to get a handle on the basic lingo. The anatomy of an earthquake. We'll cover what it is and, more importantly, where it all begins.
So here's the key thing to get. An earthquake isn't just the shaking. The shaking is the symptom. The real event is a sudden, massive release of pent-up energy in the Earth's crust. Just think of it like bending a stick until it snaps. That snap is the energy release, and the vibrations you feel are the seismic waves.
Now, this is a super important distinction. The focus, sometimes called the hypocenter, that's the actual spot, deep underground where the rock breaks. But the epicenter, that's the location on the map you always hear about on the news. It's the point on the surface directly above the focus, and it's usually where the most intense shaking happens.
So that initial snap, that energy release, is just the beginning. The real story of an earthquake's journey and its destructive power is all about how that energy travels. And it does that in the form of waves.
Earthquake energy travels in waves, and they basically come in two main flavors. You've got body waves, which, like the name says, travel right through the body of the Earth. And then you have surface waves, which ripple along the surface. Now, they're the slowpokes of the group, but they are the ones that cause most of the damage.
First on the scene are the P waves, which stands for primary waves. They're the fastest, the first ones to hit the seismographs. The motion is kind of like a slinky, a push and a pull that compresses and expands the rock. And what's wild is that they can travel through pretty much anything, solid rock, liquid magma, you name it. Arriving second are the S waves, or secondary waves. These are very different. They move the ground up and down or side to side, like if you were shaking a rope. Now here's the really cool part. S waves can only travel through solids. This is actually how scientists figured out that the Earth's outer core is liquid. The S waves just can't get through it. So while all that's happening deep inside the Earth, the actual rolling, chaotic motion we feel up here, that comes from the surface waves that are generated. The Rayleigh wave, in particular, creates a motion kind of like waves on the ocean. It's literally the ground rolling beneath your feet, which is just a terrifying thought.
Okay, with all this shaking going on, how in the world do scientists actually measure it? Let's get into the two main scales they use to put a number on an earthquake's power and its real-world impact.
This is something people get mixed up all the time. The Richter scale measures magnitude. That's the raw energy released way down at the focus. It's a pure number. But the Mercalli scale, that measures intensity, what people actually felt and how much stuff got broken. So you could have a huge magnitude earthquake in the middle of nowhere that has a really low intensity because it didn't affect anyone. Now, that Richter scale, it's logarithmic. And that sounds complicated, but it just means that each whole number is a huge leap in power. Going from a magnitude 5 to a magnitude 6 isn't just one step up. The magnitude 6 releases 31.6 times more energy. It's an absolutely massive difference, and it explains why a 7.0 can be a total catastrophe, while a 6.0 is just a really bad day. So we've covered the what and the how, but the really big question is why? Why do earthquakes happen at all? And why do they seem to happen over and over again in the same parts of the world? Well, this chart just lays it all out, doesn't it? Earthquakes are not random at all. A staggering 70% of them happen along what's called the Ring of Fire around the Pacific Ocean. Another 20% happen in a belt that stretches from the Mediterranean all the way to the Himalayas. These aren't just lines on a map. They're the battlegrounds where the Earth's tectonic plates are constantly grinding against each other. And that brings us to the number one cause, plate tectonics. The Earth's surface is broken up into these giant plates, and their constant movement, crashing together, pulling apart, sliding past each other, is what drives most of the seismic activity on the planet. Of course, you can also get quakes from things like volcanoes, but get this, sometimes we even cause them ourselves, like when the weight of a massive water reservoir puts too much stress on the rock below.
Understanding the science is one thing, but living with the consequences, that's a whole different story. Let's look at the very real impacts of earthquakes and how we try to deal with them. The shaking is just the start of the nightmare, really.
An earthquake can trigger a whole cascade of other disasters. You get landslides, you get floods when dams break. And if the quake happens under the ocean, it can unleash a devastating tsunami. In the absolute worst-case scenario, it can cause technological disasters, like the nuclear meltdown we saw at Fukushima. And these aren't just abstract threats. In Nepal in 2015, the real killer was the collapse of poorly constructed buildings. In Japan in 2011, it was the tsunami that followed the quake that led to the Fukushima disaster. And the 2004 Indian Ocean tsunami, it's just a horrifying reminder of the scale of destruction, killing nearly 250,000 people.
So, what can we do? Well, it's a multi-step process. It starts with just recognizing the risk and mapping out the most dangerous zones. Then, you have monitoring and early warning systems. Japan's system is amazing. It can give people a few precious seconds of warning. But the most important step of all is building smarter, with building codes that are designed to make structures withstand the shaking.
And this quote right here, it says everything. The ground shaking doesn't kill people. Collapsing buildings do. The fact that over 95% of deaths are from buildings that weren't built to resist earthquakes, it proves that good engineering and proper preparation are the absolute keys to saving lives. So here's where we land. We understand the forces deep within our planet. We know where the danger zones are. We've seen the devastating fallout. But being able to predict the exact time and place of the next big one, that's still out of reach. Which leaves us with the one single most important question. Are we really prepared for it when it comes?